Welcome to the deep dive. Our mission today, well, it's really to cut through some of the hype around ag. We're tackling the real technical limits of what people call vanilla RAG, the simple systems everyone started with.
That's right.
We're going deep into the advanced stuff, the architectures that are actually hopefully delivering better performance in serious enterprise settings.
Yeah, and that's critical because the main challenge, the real test for any serious retrieval-augmented generation system isn't just, finding a document.
Right.
It's solving what we call multi-hop question answering, or MHQA. That's where you need to piece together information, reason across different facts, maybe from different places entirely.
And basic vector search just falls down there sometimes.
It often does, yeah.
Yeah.
Or worse, it starts hallucinating, confidently making stuff up, especially when the query is tricky or, crucially, if the answer just isn't in the data.
Okay, so that's our goal today. We're looking at the blueprints. How do you get that mix? High accuracy, low hallucination, but without completely bankrupting your compute budget.
Exactly. And we've got sources comparing four main types: the basic naive RAG, recursive RAG, and then two kinds of graph RAG. Plus, we'll touch on the really cutting-edge stuff, this move towards Agentic RAG.
Agentic RAG sounds interesting. We'll get to that. But first, let's unpack the starting point. Before you even worry about fancy databases, our sources say a lot of the problems start right with the user's question.
Precisely. The query itself often has, noise, or it's just too vague for a simple search.
So you need to fix that first.
Yeah, and there's a whole family of techniques for this, called query translation. They aim to boost retrieval quality right at the outset. One of the simplest, but often really effective ones is the query rewriter.
Okay, query rewriter. And that's kind of smart because it accepts that, users aren't prompt engineers, right? The LLM basically pre-processes its own input.
That's a great way to put it, yeah.
So if I ask something messy like, tell me the pros and cons of vibe coding based on stuff from 2023.
The rewriter, and this is just another quick LLM call, usually it splits that up. It extracts the core keywords for the search, like vibe coding programming approach 2023. Dense. Focused.
Okay.
And then it creates a separate, clean instruction for the generation step, based on the context provided, lists the pros and cons.
So the instructions don't mess up the search itself.
Exactly. It keeps the semantic search focused.
Got it. Now, slightly different tack. Hide. Hypothetical document embeddings. This sounded really interesting. It goes beyond just cleaning keywords.
It does. With HiD, you ask the LLM to actually generate a fake but plausible answer first.
You make answer.
Yeah, a hypothetical one. And that fake answer, which is usually richer and more detailed than the original query, that's what you use for the vector search.
Huh. Why?
Because the embedding of that detailed hypothetical answer often captures the semantic meaning of the result you're looking for much better than the short, maybe ambiguous original query ever could. Just sort of predicts the shape of the answer.
Okay, that makes sense. It's bridging a gap. And there were others mentioned too, like RAG fusion, multi-query, generating multiple searches. But I wanted to ask about step-back prompting.
Step back. That's fascinating too. It basically tells the LLM, hold on, before you answer that specific detailed question, ask a more general, higher-level question first.
Like zooming out.
Exactly. Like before answering, why did my burger cost $15 yesterday?
Yeah.
It might first establish the general principle. What's the relationship between inflation and consumer prices? It sets the stage, the context, especially for that multi-hop reasoning we talked about.
Okay, that gives us a good foundation on fixing the input. Now let's get to the main event, that comparison study. 4 ARGI systems head-to-head. We need the numbers. Accuracy, cost, speed, the trade-off.
Right, but before we dive into the results, we absolutely have to clarify the 2 types of graph RAG they tested. This difference is, it's everything.
Okay, lay it out for us.
So first is KG-Graph RAG. That's knowledge graph-based. It uses explicit, predefined connections, nodes for entities, edges for relationships that are carefully built beforehand. During ingestion, it's very structured.
Structured, pre-built. Got it. And the second?
The second they call Community Graph RAG. This is much less structured up front. It actually relies on the LLM during the query to dynamically group related text chunks into communities and then summarize them on the fly.
Okay. Dynamically summarizing during the query. I can already see how that might get expensive.
Exactly. And as we'll see, that LLM-heavy refinement is where the huge costs and, frankly, some reliability issues creep in.
All right, context set. Let's hit the numbers. Overall accuracy first across all the different types of questions they asked.
Okay, so KG-Graph RAG, the structured one, came out slightly on top with 77.0% accuracy.
77%, okay.
Recursive RAG was right behind it, 76.5%. And actually, naive RAG, the simple one, scored 76.0%.
Wow, okay. So Not a massive difference in just overall accuracy then between the simple and the complex graph one.
Not huge, no. For just general performance, that marginal lift from kggraph might not seem game-changing initially.
Right, which leads to the big question. If the overall accuracy bump is kind of small, where do these fancy graph systems actually earn their keep?
Well, the answer is crystal clear when you look at anti-hallucination, specifically how they handle questions where there's no answer in the data. The hallucination test, using null queries, this is absolutely critical for trust.
Okay, moment of truth. How do they do?
kggraph RAG just crushed it, 92% accuracy on null queries.
92. Meaning it correctly said, I don't know, or refused to answer 92% of the time.
Exactly. The lowest hallucination rate by a really wide margin. That's huge if you're building something where making stuff up is just not an option, like legal or compliance.
Absolutely. 92% is a number you can take to the bank, almost. How did the others compare on that test?
Well, naive and recursive RAG were significantly worse, around 78% accuracy, meaning they hallucinated about 23% of the time.
Still not great if you need high reliability.
Not ideal, no. But then, community graph RAG, it was, frankly, disastrous on this metric. Only 28.0% accuracy.
28%. So it was hallucinating or inventing answers almost 3/4 of the time when it shouldn't have?
72% of the time, yeah.
Yeah.
It just started making connections or summarizing things that weren't really supported when faced with an unanswerable question.
Wow. Okay, if you deploy that in a regulated industry, yeah, that's not just bad, that's dangerous. That system's fundamentally broken for that purpose.
Pretty much, yeah.
Okay, that hallucination number is stark. Now, let's talk cost. The resource cost shock. You mentioned kggraph RAG, the accuracy winner, was surprisingly lean. How lean are we talking at query time? Using GPT-4o Mini, right?
Right. At runtime, kggraph RAG averaged only about 1,521 tokens per query. And it was the fastest, too, around 1.76 seconds latency.
Okay, wait. Surprisingly lean, but still 1,500 tokens per query. That implies multiple LM calls just to answer one question, right? For reasoning, traversing the graph.
Yes, absolutely.
Oh, yeah. Because naive RAG might use almost 0 LLM tokens beyond the final answer generation if it's just pure retrieval. So 1,500 is efficient only compared to other complex systems, not compared to basic search.
That's a very important clarification, yes. It shows there's an inherent overhead. You have to pay the LLM tax, as it were, for those structured reasoning steps, even if kggraph does it efficiently. Naive RAG was cheapest overall for simple stuff, as you'd expect. Recursive RAG drove costs up a bit, averaged 8,676 tokens because of its iterative steps.
Okay, understood. Now, the one we hinted at, the resource hog, community graph array.
Yeah, astronomical is the word. The average total token usage was, wait for it, 314,439 tokens.
314,000.
Yep, and the latency reflected that, over 94 seconds on average.
Good grief.
And that massive cost comes directly from that dynamic LLM-driven summarization and refinement we talked about. It's essentially making dozens of expensive LLM calls for every single user question to build those communities and summaries on the fly.
Okay, if my boss saw a bill for 314,000 tokens for one query, my project's getting canceled. That's a massive wake-up call for anyone thinking about these, super dynamic, LLM-heavy architectures.
It really is. So the takeaway here seems pretty clear. kggraph RAG offers the best balance, especially for those high-stakes MHQA tasks and, critically, for low hallucination.
Right.
But there's a catch. It has an initial construction cost. Building that structured knowledge graph in the first place took about 3 million tokens in the study. It's a one-time cost, but it's significant.
So the trade-off is bite the bullet on the upfront build cost for kggraph if you absolutely need that 92% anti-hallucination rate, like for legal tech, finance, compliance. That upfront cost buys you trustworthiness later.
That seems to be the calculus, yes. Because once it's built, it's efficient and trustworthy at query time.
Okay, the numbers paint a picture. kggraph wins on trust and runtime efficiency once built. But why? Let's dig into the structural difference. Why does the graph structure give it that edge, especially over just retrieving text chunks?
Well, the fundamental advantage is that knowledge graphs explicitly model entities, concepts, and critically, the relationships between them, nodes and edges.
So it's not just finding keywords, it's understanding connections.
Exactly. That structure is what enables reliable, multi-step reasoning needed for complex questions inference, comparison across different points. And importantly, the graph structure allows for really clear source traceability. You can often track an answer right back to specific nodes or edges in the graph.
Which is key for grounding the answer and preventing those hallucinations.
Precisely. It helps keep the LLM tethered to the actual source data.
Okay, that makes sense for a single graph source. But what if your information is scattered? Say you have some data in a graph database, but other relevant stuff is in a traditional SQL database. How does RAG handle that complexity?
Yeah, that's where simple semantic search across everything starts to break down. You need routing. Yeah, basically figuring out which data source is the right one for this specific question. And often, this means translating the user's natural language query into a query language that the specific database understands.
Like text to SQL.
Exactly. Text to SQL for relational databases. Or text to Cipher if you're querying a Neo4j graph database, for instance. The router directs the query intelligently instead of just doing a blind vector search everywhere.
Okay, so routing plus translation is key for multiple sources. And what about indexing? We saw mentions of going beyond just linear text chunks.
Right, that's about hierarchical indexing. There are techniques like Raptor, that's recursive abstractive processing for tree-organized retrieval.
Raptor, okay.
The idea here is to index the data at multiple levels of abstraction. You index the small, detailed chunks, obviously, for specific facts, but you also create and index higher-level summaries and summaries of summaries recursively.
Like building a table of contents on the fly.
Kind of, yeah. It helps the system retrieve relevant information, whether the user asks a really broad thematic question that needs a summary or a super specific granular question that needs a precise detail. It improves semantic coverage.
Interesting. Okay, so we've covered query fixing, benchmarks, structure, routing. Now let's look ahead. You mentioned Agentic RAG. This sounds like where things get really dynamic.
It really is the next evolution, I think. Agentic RAG basically integrates autonomous AI agents into the RAG pipeline itself.
Autonomous agents? Doing what?
They act as orchestrators. They can do complex planning. They can decide which tools to use. Maybe vector search isn't the right tool. Maybe it needs to hit an API or do a web search. And crucially, they handle multi-step reasoning and validation. They make JAG adaptive.
So instead of a fixed pipeline retrieve, then generate the agent decides the steps.
Exactly. It might decide, do I even need to retrieve external knowledge for this question? If yes, okay, which tool is best? VectorDB web search. A specific database via text to SQL. And critically, after retrieving something, the agent can validate it. Is this retrieved info actually relevant to the user's query?
That validation step sounds key. So what happens if the agent retrieves stuff and decides, nope, this isn't useful?
That's where you get these active or corrective RAG flows. The agent doesn't just give up and say, sorry, can't help. It adapts.
It tries something else.
Yes. For example, in what's called corrective RAG, or CRAG, if the agent grades the initially retrieved documents as, say, irrelevant or insufficient, it might dynamically decide to trigger a web search to pull in external up-to-date context before attempting to generate the final answer.
Okay, wow. So it's not just one shot anymore. It can become a cycle, retrieve, validate, maybe retrieve again differently, then generate.
Precisely. It moves RAG from that static linear process to a dynamic, potentially cyclic self-correcting flow, all orchestrated by the agent.
That sounds incredibly powerful, but also potentially complex to manage.
Oh, absolutely. It adds layers of complexity, but also huge potential for robustness and accuracy.
So, wrapping this all up, what's the big picture for someone designing these systems? We've seen KG Graph RAG hitting that sweet spot for high-trust, high-stakes applications, despite the setup cost, mainly due to that amazing 92% anti-hallucination score and decent runtime efficiency.
Right. The trend seems clear. We're moving beyond just retrieval. We're layering reasoning, planning, and this dynamic flow logic on top of retrieval. That's agentic RAG or modular RAG systems.
So the problem isn't just finding the right document anymore.
No, it's much more about dynamically validating the context you find. Routing the query intelligently, text to SQL, text to Cipher are still super relevant here. And above all, ensuring the final answer stays grounded and faithful to the underlying sources. That's the name of the game now.
Which brings us to a final thought for you, the listener. We saw that basic naive RAG and recursive RAG actually got perfect or near-perfect scores on simpler, fact-based inference questions, and they're way cheaper to run and build.
Yeah, for certain tasks, they were surprisingly good.
So the really tricky question for an architect is, When is the extra complexity and that significant upfront build cost of something like KG-GraphRag truly worth it? Is that near-perfect handling of null queries and complex reasoning worth the investment compared to the cheaper options that work well for simpler cases? That's the tough resource decision you face today.